In this first question, we are finding the sample points in the sample space. So we're tossing a fair coin and we're rolling a fair die. So a couple ways to do this. You can use an outcome table, which is what I'll do first here. And so we list the outcomes on the coin on the edge here, and then we'll list the outcomes on the die across the top, 1 through 6. And then we combine them sort of like a multiplication table. So heads and a 1, heads and a 2, and etc. down the row. So we got heads 3, heads 4, heads 5, and head 6. And then we do the same for tails. So tails and a 1, tails 2, all the way down to tails 6. So there are 12 outcomes. Are they equally likely? Yes, because each of the coin and the die are fair, so that makes each component outcome equally likely. Now, another way to get these would be to do a tree diagram. It'd be a little bit messier, but you could flip your coin. You could get heads or tails. And then roll your die. So you could get 1, 2, 3, 4, 5, 6. And then the same for tails, 1 through 6. So then you'd have heads 1, heads 2, down to head 6, tails 1, tails 2 to tail 6. So same outcomes either way, same sample points. Next up, we've got a Venn diagram. We're given probability of the sample point E1, E3, and E5 are all the same at point 2. Probability of E2 is 0.1. Probability of E4 and E6 are both 0.15. And we want to find the probability of the event A. So A includes E1, E2, and E3. So we add those probabilities. So probability of E1, so add the probabilities of the sample points in the event, plus probability of E2, and plus probability of E3. So E1 is 0.2, E3 is also 0.2, and E2 is 0.1. So 0.2 plus 0.1 plus 0.2, which makes 0.5. Probability of A intersect B, so the overlap or intersection of A and B only includes at one sample point E2. So this is just probability of E2, which is 0.1. A union B, so A union B here includes the sample points E1, 2, 3, 4, and 6. So everything except 5. So probability of E1, 0.2. Probability of E2 here, 0.1. So add the probabilities of the sample points in the event. Probability of E3, another 0.2. E4, probability 0.15. And then E6, probability of 0.15. So 5 here and another 3, that is 0.8. Probability of B complement. So that's the sample points that are not in B. So if you're not in B, so B includes 2, 4, and 6. So not in B is going to include 1, 3, and 5. So this is probability of E1 plus probability of E3 plus probability of E5. One, 3, and 5 all have probability of 0.2. So that's 3 times 0.2, which is 0.6. And then A complement intersect B. So you're not in A. So inside A is this here. So not A is outside A, which is that and that. That's the part that's outside A. And we want to be inside of B. So if you're inside of B, that's going to mean that you're in the right circle. And then the intersection is going to be both the yellow and the shading, which is going to be E4 and E6. So we back that up. So this is probability of E4 plus probability of E6. And sample point 4 and 6 both have probability of 0.15. So 0.15 plus 0.15, 0.3. And then probability of A given B. So by definition, that is the probability of A and B divided by the given probability of B. So probability of A and B, we've got that right here, 0.1. And then probability of B, well, probability of B complement was 0.6. So the probability of B would be 1 minus 0.6, 0.4. So that's 1 divided by 4, 0.25. So that's Venn diagrams. Next up, we have a bag with some marbles in it. We have 4 solid colors. They're numbered 1 through 4. We have 8 cat-eye marbles, and they're numbered 5 through 12. We're going to draw 1 marble from the bag, find the following probabilities. So probability of the marble is a cat-eye. So there are these are all equally likely that we would draw any one of the marbles. So we can use desired outcomes out of total outcomes. So the total outcome is 12 marbles. And there are 8 of those marbles that have cat eyes. So 8 out of 12. And you can reduce that if you want. The marble has an odd number on it. So there are 12 marbles total. And there are 6 odd numbers. 1, 3, 5, 7, 9, 11. So 6/12 or 1/2, 0.5. Marble has an odd number on it and is a solid. So your solids are 1 through 4, and the odd numbers are going to be 1 and 3 out of 1 through 4. So there are 12 total, and there are 2 solids that have odd numbers. So this is going to be 1 and 3. So 2/6 or 1/12. And then probability, the marble is an even number or it's a cat eye. So for this one, we can use the addition rule here. So this is going to be probability of even plus probability that it's a cat eye, and then minus the probability of the overlap, even and a cat eye. So our even marbles, there are 6 out of 12. Plus our cat eyes, there are 8 out of 12. But then we double counted the even cat eyes, which were 2, 4, 6, and 8. So we have to subtract those 4 out of 12 out. And so that leaves us with 10 out of 12. 10 twelfths. Next up, we've got a table with some data here. We had 172 people surveyed. We asked them which burger they liked the best, Big Mac, Whopper, or Wendy's single. We've got our row totals here and our column totals here. So we select a person at random, so that would make it an equally likely sample space. What is the probability the person prefers a Whopper? So desired out of total here. So the total is 172. And the people that preferred the Whopper is going to be that column total of 58. And what is the probability the person is female and prefers a Big Mac? So the females are this row right here. And the people that like the Big Mac are that column right there. And notice the overlap, 30. So and is the overlap. They're in both. So that would be 30 out of 172. And the person is male or prefers Wendy's single. Okay, so that's going to be union rule. Okay, so this is going to be probability that they're male plus probability that they prefer the single, S, and then subtract out the overlap, male and single. So the males, total males were 78 out of 172. And then we add those that prefer the single, which is 69, that column total out of 172. And then subtract out the overlap. So the males are this first row. And those that prefer the single, that last column, 55 are in the overlap. So subtract out 55 out of 172. And then if you do the math there, you will get 92 out of 172. Person is a female if we know they prefer the Whopper. So if we know, that's a conditional probability. So it says probability of female given that they prefer the Whopper. So remember, one way to think about that is the given condition restricts your total outcomes. So it's given that they prefer the Whopper. So they have to be in this column. That's a given, and that's 58. And then out of those 58 people, we want to know how many are female. Well, 50. So 58 in the denominator, and then out of the 58, 50 are females. So 50 out of 58. And we could reduce that if we want. So again, this is female and they prefer the Whopper, and then this is the number that prefer the Whopper. Person is male if we know they do not prefer the Whopper. So this is probability we are male given W complement, so not Whopper. So again, that given condition determines your total outcomes. So the people that prefer the Whopper are right there, 58. And so your complement is everybody that's not included in that 58, which is 45 and 69. Or if you want, 172 minus 58. So that's your denominator. So that's these people here and these people here. So out of those 4 column entries, we want to know how many are male. Well, 15 there and 55 there. So 15 plus 55 in the numerator. So that makes a total of 70 in the numerator. And then in the denominator, 114. And then are M and F independent? So male and female, are they independent of each other? And then are M and F mutually exclusive? So mutually exclusive means separate, and male and female, those 2 rows are separate. So this one's definitely a yes, and that's because there's no overlap between those 2. So male intersect female equals the empty set, no overlap. And then independence, remember that one's a little tougher to check. That one you have to look at the given probability and the conditional. So for example, probability of male, and then compare that to probability of male given female. So the probability that they're a male, so males total we had 78 out of 172. And then probability they're a male given that they're a female. So you only consider the females, which is 94, the second row. And out of those 94, how many are males? None. So this is 0. So these guys are not equal. So are they independent? No, not independent. So if they were independent, this probability would not change. One event would not have an effect on the other, but being female certainly has an effect on being male. If you're one, you can't be the other. Next, we're using a probability tree to solve our problem. So performance of sports teams can depend on where the game is played. So Olivet plays 40% of its games at home. And then that means the rest are away. Olivet's basketball team has a 70% chance of winning a game that's played at home. And then if the game is played away, the probability drops to 55%. So let's let home, H be the event home game. And then H complement is going to be an away game. So you can use H complement or you can use A for away. And then we can either win the game or not win the game. So we've got W is going to be that we win. And then W complement is we don't win the game, we lose the game. And let's represent that with an L. So first level in our tree, we can either play a home game or an away game. If we play a home game, we can either win or lose. Playing an away game, we can either win or lose. So now let's fill in our probabilities. So 40% are home games. So this is 0.4. And that means that away games are 60%, right? 1 minus 0.4, 100% minus 40% is 60%. Now, if they play a home game, their chance of winning is 70%, 0.7. So that means they've got a 30% chance of losing. These have to add up to 1. If they play an away game, then their winning probability drops to 0.55. And 1 minus 0.55, 0.45. So we've got home and win, home and lose, away and win, or away, lose. Those are our 4 possibilities. And then the probabilities, you multiply in the branches. So 0.4, 0.7, 0.28, here 0.4, 0.3, which will be 0.12, 0.6, 0.55, that is 0.33 to 2 decimal places, and then 0.6, 0.45. And that is 0.27 to 2 decimal places. What's the probability of a win here? So probability of a win, overall win, well, there's 2 ways they can win. It could be a home game and they win, or an away game and they win. So this is going to be the probability of home and they win, or plus probability away and they win. So home winning game, 0.28, plus away and they win, 0.33. So we add those guys up and get 0.61. Next up, we are counting some sample points here. So how many telephone numbers are possible, including our area code? If the area code can't begin with a 0 or 1, the middle number of the area code must be 0, 1. And then the local portion has to start with 93. Well, we can do counting with slots here. So we've got our area code, which is 3 digits, and then the first 3 local digits, and then the last 4 local digits. So we put the number of possibilities for each step. So the area code can't begin with 0 or 1. So we don't have 10 choices here. We've got 8 choices there. And then we'd have 10 choices for each of the remaining digits of the zip code because they allow repeats. And then it has to begin, the local portion has to start with 93. So we've only got 1 choice here and 1 choice there. They have to be 93. And then let's see here. The area code can't begin with 0. Oh, the middle number of the area code must be 0, 1. So only 2 choices allowed there. Sorry about that. And then that last digit, no restrictions there. And then the local portion has to start with 93, but no more restrictions, so these are all 10s. And then we multiply those possibilities. We will get 16 million. If you plug that in the calculator. So 16 million phone numbers with area code. Some more counting here. Number 7, how many different 5-element samples can be drawn from 200 elements? So samples there, order does not matter. This is combinations. So you are just going to do 200, choose 5. And you can just use NCR on your calculator. That's under the probability menu, remember. So this is going to be 200 C5. And if you plug that in on the calculator, you should double check it. 2535, 650, and 040. So let's see, what is that? 2,535,000,000. If random sampling is used, what's the probability of selecting any particular sample? Well, all these samples would be equally likely because we're using random sampling. So the chances of picking any one sample would be 1 correct sample divided by the total number of samples. So that's over 2535, 650, 040. Desired out of total. Problem number 8, we're classifying some random variables as discrete or continuous. Remember, discrete is something that's countable, 0, 1, 2, 3. Continuous is something that's measured, takes on every value in a range. So the time it takes a student to get through the lunch line at Ludwig. So time is infinitely divisible. It could be anywhere between, say 1 minute and 20 minutes. So that one's continuous, can take on any value. The number of A's on the Math 241 final. So you could have 0 A's or 1 A or 2 A's. Those are countable. So that's discrete. Number of felonies committed per day in the city of Chicago. 1 felony, 2 felonies, 10 felonies. Those are countable. That is a discrete. Amount of carbon methane produced by a cubic foot sample of trash in a year. So that is something that would be measured usually by weight. So they would say number of grams of carbon, and weight is infinitely divisible. That's going to be continuous. So this would be carbon/methane. And number 9, we have a probability distribution now. Random variable is number of years that a person with a transplanted heart will survive. So here's number of years, 1 through 6. Here's the probabilities. We want to compute mean and standard deviation. first. So remember that the mean here is the sum of x times probability of x. So what we need to first do is put that information in a table. So let's give ourselves a little bit of room here. So let's make a table here, and we've got x column and probability of x, and then x times the probability of x, and then x squared times the probability of x. So remember, that's called our extensions table. So our years 1 through 6. And our probabilities, 0.35, 0.22, 0.18, 0.15, 0.06, and 0.04. So x times probability of x, so 1 times 0.35, 0.35, 2 times 0.22, 0.44, and so on, all the way down. X squared times probability, so 1 squared is 1 times 0.35, 0.35. 2 squared is 4 times 0.22 is 0.88, and so on, all the way down. So why don't you fill in the rest of these and pause the video, and then come back and double check your work. So for the rest of that x times p of x column, you should get 0.54, 60, 0.30, 0.24. Total is 2.47. Your probability column should always total to 1. The rest of the x squared probability column, 1.62, 2.4, 1.5, 1.44, totals to 8.19. So our mean here is the sum of the x p of x column. That's right here, 2.47. And then standard deviation, well, variance here is the sum of the x squared p of x column. And then you subtract the mean squared, so minus mu squared. So that's going to be the sum of the last column, 8.19, and then minus our mean, 2.47 squared, which gives you 2.089. And that's sigma squared, that's the variance. So sigma is going to be square root 2.089, which is approximately 1.45. What is the probability a random transplant patient will survive more than 2 years? So this is saying that we are looking for the probability that the random variable x is greater than, more than 2, so greater than 2. So that would be 3, 4, 5, or 6. So this is, and actually it's a little bit easier to just do the complement event here. Could add these 4 probabilities, or you could say, well, that's 1 minus the probability that x is less than equal to. So that'll be 1 minus, and then probability x is less than equal to is 1 or 2, so 0.35 plus 0.22. Which is 0.43. And then interpret our mean. So our mean or expected value, that's going to be the expected survival time, or the mean survival time of a randomly chosen person. So this is going to be the mean or expected survival time. So that's discrete random variable. And then in problem 10, NASA's determined there's a 0.05% chance that the booster system would fail on a particular model of booster for a space shuttle. They test 100 boosters. Compute the probability that one booster will fail. Well, this is binomial because it's pass-fail. It either works or it doesn't. So these are binomial probabilities. So we want to find first in part A here, we want to list N and P. And then in part A, we want to know the probability that let X be the number of boosters that fail. So this would be one booster will fail. So this is going to be probability X equals 1. And if we use we'll use the formula, and then we'll check it with the calculator here. And then in part B, what is the probability that more than 2 will fail? So this is probability that X is strictly greater than 2, where X is the number of boosters that fail. So N, the number of samples, is 100. There's a 0.05% chance the booster will fail. So 0.05%, we move the decimal to the left 2 places, 0.0005. So probability X equals 1. So remember that probability of X successes in a binomial experiment is N choose X, and then it's P to the X, 1 minus P to the N minus X. So probability that X equals 1, this will be 100, choose 1, and then times 0.0005 to the first power, and then 1 minus 0.0005 is 0.9995, and then that gets a 99 power. So that would be using the formula. But we can use a binomial PDF here. You can also do binom PDF, because calculator will compute these for us. And that's what I'll have you doing on the test, is binom PDF. And then it's NPX. So N is 100 trials, P is 0.0005, and then we want 1 success. So either one of those expressions, when you enter it into the calculator, you will get 0.0476 to 4 decimal places. And then probability X is greater than 2. So greater than 2 would be 3, 4, all the way up to 100. So either 3 fail, or 4 boosters fail, or 5 or 6, all the way up to 100. So, well, it's going to be easier to look at the complement probability. 1 minus probability that opposite of greater than 2 would be less than equal to. And less than equal to there, we can use binom CDF. So this will be 1 minus binom CDF. And then it's N, P, and X. So N is 100 boosters tested. Probability of failure is 0.0005. And then it's up to 2. And if we go ahead and enter that into the calculator, we will get scientific notation. So I'll actually get here 1.949 times 10 to the negative 5th. So, and let's enter that one in just for practice. So 1 minus, and then we second variables, and then binom CDF. Scroll down. Binom CDF there. N is 100, P 0.0005, and X is 2. Paste it, and there's our 1949 times 10 to the negative 5th. And then in problem number 11, we are given here that these are binomial random variables. So all of this is going to be binomial PDF or CDF. So remember, PDF is when you've got an equal, like this one will be PDF. All the others will use CDF. So sample size is 10, N is 10, P is 0.4. Compute probability X less than or equal 3. So that's going to be binom CDF. And that's less than or equal 3. You gotta write everything with a less than equal. So N is 10, P is 0.4, and then up to 3. And if you enter that into the calculator, you get 0.3822. And then greater than 9, we have to write that in terms of a less than equal, because CDF is a less than equal probability. So the opposite, 1 minus the opposite probability, which would be probability if it's not greater than 9, it's less than or equal 9. So that's going to be 1 minus binom CDF. And that will be 10, 0.4, and 9. Plug that guy in the calculator, you'll get 0.0001. And then probability between 2 and 6, and not including 6, but including 2. So this would be probability that X is equal to 2, 3, 4, or 5, but not 6. So what we could do is do less than or equal 5, and then subtract out 0 and 1. So less than or equal 5 would be binom CDF, 10, 0.4, 5. So that's probability of 0 or 1 or 2, 3, 4, or 5. And then subtract out binom CDF. And then this will be 10.41. Give ourselves a little more room here. So this is probability 0, 1, up to 5. And then we're subtracting out probability 0 or 1. And that'll leave 2, 3, 4, 5. So if you enter that in the calculator just like that, you will get 0.7874. And then probability X equals 4, so that'll be binom PDF. And then 10 is our total, 0.4 is P, and then 4 successes, quote unquote successes. So again, through the second variables menu, if you enter that in, you get 2508. And then mean and standard deviation. So these are easier with binomials. So remember, mean is just n times p. So that's going to be 10 times 0.4, which is 4. And then the standard deviation is square root np 1 minus p. So square root 10 times 0.4 times 0.6. And if you enter that into the calculator to 2 decimal places, you get 1.55. So that should get you set with pretty much everything that's on the Canvas portion and the written portion of the test.